So that's that. And okay, so for this lesson, we're going to cover like classification, using logistic regression. And how we're going to do it, we're going to split it into two parts. So the first part I'll walk through with you guys. We're going to do predicting whether a patient has diabetes or not. And then we're going to go over like Tensorflow as the kind of theme of today, why it's important. We're going to use it, and I'll walk through like the steps on that. Then part two is going to be classification on the MNIST dataset. And in case you guys haven't heard of MNIST, it's a dataset of handwritten numbers, 0 through 9. And then we're going to leave you guys to do that part using what you learned from part one, so that you guys can apply that to recognize digits. And we'll cover how that data is like oriented and everything too before we set you loose. But that's the general plan. So first, we have this data set that was in the GitHub repo. All you have to do is run these commands. But what we have is for each patient, we have number of times they got pregnant, glucose concentration, blood pressure, all these features of them. And then at the end, we have a label that denotes 1 for they have diabetes and 0 for they don't. And we're going to build a predictor to correctly predict this. So moving on, we have 8 features. I'm just setting this variable to use it later. Here's kind of what the labels look like. It's just a string of 1s and 0s, diabetes, not diabetes. However, we can't just use this in our model, and here we're going to explain why. So this function takes each one of these 1s and 0s and it it makes it categorical. I don't know the sorry. So what that means, so if it's so you see this first sample is a 1. So it'll put it in this position, and then so the second position there. And then the second sample is a 0, and you see it puts the 1 in the first one. So depending on the position, denotes whether they have diabetes or not. And we need this just so we can run the TensorFlow operations.
Yeah. Actually, if you explain how it works with like Softmax or with MNIST, once we have like 9 things, that might be useful. Like one-hot encoding stuff.
Yeah, so it's also scalable. So let's say we have more than 2 options. It's not a binary problem. So for MNIST, we want to classify digits from 0 to 9. That's 10 options. We can just scale this up. So if we want to classify 9, we'll put it in the 10th spot of the array. We'll put the 1 there, and then 0s everywhere else. If we want to classify 1, we'll put it in the 2nd spot, 0 indexing, and 0s everywhere else in the array. And these are what the model's ultimately predicting. These are the arrays it wants to get right.
And if you don't pass in the number of classes, it just automatically calculates it from the...
Here? No, you have to give it this.
Oh, because it says if not, NB classes.
Where?
Like the
oh,
there.
Yeah, no. I'll be honest, I took this code from somewhere else.
Oh.
And that's another point I wanted to make. Moving on, when we use other libraries, they have functions that do this for you. But I didn't want to have all this complicated stuff. Okay. So I just wrote it out. You don't have to worry about the inner workings of this. Just know what it does. Because people have already written these for you. It's not something you should be worried about. I even just found this online. I was able to reformat it for this. So these are final things we're predicting. So there's 768 total samples. That's what this first index means. So then to get the actual training data, we want the 8 features. So going back up here, we want these 8 features. We're ultimately going to do logistic regression on these to predict this final one. So you can see we have 768 samples, each with 8 different features. And like in the linear regression, we're going to do some normalizing. So we can kind of compare apples to apples, so everything's scaled the same way. Nothing will skew the model anyway. So these are kind of what the normalized inputs look like. Just some good pre-processing steps that will help the performance. I split the data into train and test set. So if you guys remember, we really want to do this because the point of making these models is so that they can perform well on data it hasn't seen. That's the ultimate goal. So if we train it on data it's seen and then test it on that same data, that's not an accurate measure. So we want to siphon off a portion of it so that we can get like a good measure of how well we're actually doing. So now TensorFlow. So before that, let's visit their website. So you guys probably heard of TensorFlow. Like it says, it's open source software library for machine intelligence. But why is it so big? So it's big because it's open source and it's run by Google. So that means it's a well-run platform. A lot of things you can do. You can pretty much do anything, actually, if you have the time to go research and look at all the special functions they have. But it's really like one of the go-tos for machine learning, like implementations and trying out new models these days. And in fact, people actually built higher level, like, I don't know if you guys heard of CAIS. It's a higher level API on top of TensorFlow. So it's used everywhere. They also have something called TensorFlow serving, where you can like serve a model on their servers. They have whole systems where you can like export it to run on your apps and stuff. Yeah, it's used everywhere. And so going through this TensorFlow, I recommend if you guys want to get into it. These tutorials are really helpful. The whole getting started part. They also have tutorials on all like the key algorithms. So like classifying images, they have a tutorial on that. Doing translation, English to French, They have a whole sequence of how to do that and implement it using TensorFlow, which is really helpful. Because it's well documented. And then again, if you want to like search any functions, like here's like an example thing you might want to see what it does. It has all the specifications. You see like there's a bunch of stuff it can do. So you'll probably be visiting this a lot when building your own models. It'll be painful at some points, but it'll pay off just because of the power of it. It can do a lot. So moving on, that's TensorFlow. Now, we're going to get into a technique called batching as well in this lesson. So if you remember the linear regression module, what we did was we actually ran gradient descent on each sample. But actually, that's not what's really done, and it's kind of inefficient. So what most people do, and the kind of the norm in the machine learning community, is like using batches. So what that means is that we'll take 16 samples at one time, run the model, calculate the error, average the error over those 16, and then update our gradient descent. And what this allows us to do is train quicker. Although the accuracy metrics are less accurate, I guess your loss functions are not really, they're averages. It's shown that it can still perform really, there's no difference, batching. So it's really a step everybody does to speed things up. And what this function does is it just takes our train set and it grabs batch size, so that number, whatever that number is, it grabs that many images from the train set, and they're randomly chosen, and then we'll run those through the model. And just as another side note, when we get into other libraries and stuff, you usually won't have to write these. They'll have it implemented, so you can just say like, oh, give me batches of 16 or 32. You can just like put that as a parameter, but we'll visit that later. So it's that. So now we're going to get into actually coding in TensorFlow. So the first thing we're going to talk about is placeholders. And so the way TensorFlow works is that there's really two main types of operation or variables you can set. One is placeholders and one is variables. And as you kind of think intuitively, variables you can change. So these are like the weights and biases that are going to change when you do gradient descent. But placeholders are designated to things like inputs. Those aren't going to change. Those are static. So that's generally how things are segmented. So to start things off, let's define our input. We're going to make it a tf.placeholder, tf.float, 32, and then size none by 8. Yeah, of course. that good? Sweet. And so basically, what all this means is that, so TensorFlow is a very specific language, and that's why people have made APIs that sit on top of it. And so like things like this where we have to define tf.float32, it can get kind of annoying, but it's necessary in order for TensorFlow to do its operations. It requires that type of value. So we have to specify that. The whole none by 8 business. So none is used as kind of like let's say you don't know how many dimensions are going to be in that spot. You can use none to say like any, you know. And in our case, it's the number of samples. So although we do know ahead of time, let's say we got more data, you know, we want to keep that variable. So none just basically whenever you see that, and like most languages too, I mean like your choice, user choice. And then we're going to do 8 here because we have 8 features. So if you remember, like we had the blood, something about blood. I forget the other ones, but they have to do with general health. So yeah, we have 8 of those, so that's why we're defining that there. The next thing, we're going to define our first variable using tf.getVariable w shape equals 8, 2, initializer equals tf.contrib.layers.xavier initializer. All right, so to make a variable, we're going to cover like the 2 ways you can do it. So this is one of the ways where you do tf.getVariable. This is kind of like a constructor. That's really what it is. So it just creates this variable, creates memory for it. You give it a shape. So in our case, we're giving it shape 8 by 2 because we have 8 features, but we want to whittle it down to 2 options. So diabetes, no diabetes. So that's why that's that. And in TensorFlow, you have to define the initializer yourself. So we're going to use from their library the Xavier initializer. And that is just a good way to initialize weights. A lot of people use it. If you want to learn more, you can just look it up. But just randomly initialize it so that it trains well. So you have to define that. OK. So next, we're going to make our bias. So if you guys remember in the lesson, whenever we do like these regression things, we have to have both weights and biases. And we train both of them. So the biases are also going to be a variable. And sometimes you might see it written like this too. So just tf.variable. This is kind of like the simpler way to do it. This is how TensorFlow does it in their tutorials. There's a slight difference. I forget exactly what it was, but it's how it constructs it in memory. In general, you want to actually use this top one. So you see that more, but I just wanted to show you guys that this also works. And how we're going to initialize it with all zeros, because that's the best practice. And it's going to be size 2, because of our output to correspond with this dimension. So that's that. And then we're going to want to define our decision process now. So if you guys remember, in the curriculum, we talked about the sigmoid function. So I actually think I have it. So this is the sigmoid function. It squashes your inputs between 0 and 1, which makes it really good for classification. Because you can just say like, oh, if it scores above 0.5, make it a 1. If it scores below 0.5, make it a 0. It's a really nice function for that.
And we're appending this after the...
Well, we're actually not going to use the sigmoid directly. We're going to use something called the Softmax function, which is kind of an extension of the sigmoid. And actually, when you use the Softmax on just 2 choices, 0 or 1, it's like mathematically proven to be the sigmoid function. But speaking of Softmax, why we're going to use it is because, one, it's really popular, but that's not why. But it's really good for if you want to do classification tasks. So how it works is So here you have 3 scores. Your linear regression part outputted it, so w times x plus b gave you these 3. But what it does, it will actually transform these into a probability distribution. And the way it does this, it uses this logistic function. And this term right here is essentially a normalizer. That's what it is. So it normalizes it so that these all add up to 1. And what the softmax function allows us to do is, like you see here, this is not just 2 inputs. It allows us to choose the best input over as many as we want. So let's say we have to do 100 decisions. We want to choose the best decision. This will give us a probability distribution marking like which choice is the best. And so, and it's also, you'll see it. It's pretty much the final layer of like every classification task. But we'll get more into the math behind it in the next lecture. But I figured I would show it to you guys now because we're doing classification. So to make this sigmoid, or to make this softmax function, we want to do y. So y is going to be our final score output, the nn. So nn is just neural net. It's just the library. We'll get more into it next week, actually. That's just the library it's coming from. .softmax tf dot matrix multiply by x w plus b. So as you recall, we got to do this linear transformation portion. So that's the matrix multiplication. And then we're going to apply this softmax function, as we saw here, but with only 2 inputs. So pretend there's only 2 here. And it's going to map them into a probability distribution that adds up to 1. And then the way we'll choose them is we're going to choose the higher score. So if it's saying the 0 spot is better, that means it thinks it doesn't have diabetes. If the 1 in the 1 spot is bigger, it means it thinks it has diabetes. So that's a general consensus of how that works. So now we can run this cell. I can't because I didn't run anything else. Sweet. This is just a sigmoid function. I just wanted to give you guys another visual cue of what it does. Not too important for running the model. Okay, so next we want to train our gradient descent. So in TensorFlow, we're going to define like what a train step is. So every time it steps through this loss function, it's going to do the gradient descent optimizer, and TensorFlow has that in their library, which is really nice. And we're going to take a learning rate of 0.01, and we're going to minimize the loss function, which was defined right here. And sorry, I actually skipped over it, but we'll go explain it right now. So this is the cross entropy loss. So it does look a bit different from what you saw in the curriculum because TensorFlow has these really nice reduce sum, reduce mean operations. What basically, so for each axis in a matrix, it finds the sum and it finds the mean for that specific row or column or axis. So it's just basically the cross entropy implemented in TensorFlow. So we're going to minimize that. And so in TensorFlow, in order to actually run any of these things, to run any of your optimizers, to train your model, you have to start a session. And so we're going to do ses equals tf.interactive session. There's also a regular session. You can use either of them. And what we also have to do is we have to initialize all of our weights in our biases. So as you recall, like we did specify like what they should be, but they're not actually put into place until you run the session or initialize or run the initializers. So that's what that does, and you have to do this, every time. So here we're going to actually run gradient descent 10,000 times, and we're going to use our generate batch function that we took from earlier. And so we can get some batch x's, batch y's, which is basically our training samples and our labels. We're going to get them randomly. And then to actually run the gradient descent, you do ses.run, the train step, which we defined up here as a gradient descent optimizer. and then you have to feed it in a dictionary of training samples and labels. So in our case, our dictionary is going to be, so our x that we're feeding the model, so x corresponds to our placeholder, right? And that's going to be these batches we produce, and then our label is going to be that as well. So now that we run our gradient descent, we want to find out how well it did. So to do this, we're going to keep track of how many predictions we got right, and we're going to use the tf.equal function. And so for the prediction, remember it's predicting to a matrix of size 2, right? If it has 2 spots for it, denoting whether it thinks it has diabetes or not. And so it's going to take the argmax, which is just the maximum value for the prediction, and then for the actual. So y underscore is that's the ground truth, and then these are our predictions. And it's going to see how many of them are equal. So it's going to see how many. So like, let's say it predicts in the first spot a score of 0.7, and the second spot 0.3. Then it's going to say it's the first spot, and it's going to see if the first spot is corresponding to the actual ground label. And so this generates a list of booleans. And then from that list, this is kind of a funky way to do accuracy, but we have a list of how many we got right. We're going to just basically take the mean of it. So we get a final accuracy measure. And another thing to know in TensorFlow, which is also kind of annoying, is that you kind of have to cast everything so that I can work with it. So our NumPy arrays actually come in, since we're using pandas, they come in as float 64s. This is just how pandas operates by default. And so to actually compare them and to do operations on it, we got to cast them to float 32s because that's what TensorFlow needs to operate. So we do that. And then finally, to get a percentage score on the accuracy, we got to do another feed dict. We're feeding our test set this time that we defined earlier, and ultimately seeing how well it does. So we got 77.9% accuracy. It was pretty good. Any questions on this? Sweet. It all ran? Nice.
Oh, I had a question.
Yeah.
So usually, I've been always told that we're not supposed to use Python loops.
In here?
Just like Python loops in general, just really slow. I was just wondering, is this a case where you would use it, or?
Well, I don't know if this is the best answer, but my first thing that comes to mind is that to actually run these training steps, sometimes it'll take longer than to do the for loop iteration. But I've seen them done. In TensorFlow, you do have to write more out, which is another bummer of it. You have to write out.
Yeah.
This is not normally the way it's done, but we definitely simplified the process. I'm sure there's other optimization methods people use. But yeah, this is just kind of get a feel.
Epochs up there, right?
Yeah. No, this is the number of steps.
Oh.
Yeah, so it's not even. So what will actually happen when you get deeper into TensorFlow, into these other APIs that run TensorFlow, is they'll have this all figured out for you. Just say how many epochs do I want it to run for? And then it'll automatically choose for how many times it should update to find the optimization. So they incorporate what they call a lot of best practices so that we don't have to worry about specific numbers of learning rate and all that other jazz, Yeah, so this is a very simplified approach to it just to get an understanding of how this gradient descent is updating, but that is a good point. And it's something you won't really, I don't think you'll have to worry about in terms of efficiency later, just because the amount of libraries that will do it for you, where you can just specify how much you want it to run for, your batch size and all that. So yeah, any other questions? Cool. So now we're going to go into the portion where you guys do the work. And that's going to be the, where is it? MNIST set. So yeah, our basic theory we're trying out this time is we want to get you guys actually coding in TensorFlow and applying what we just went over, how to like do placeholders, weights, and getting comfortable with them on just a different problem, just so you can solidify your understanding. So what this problem is MNIST. And so here's what MNIST looks like. I know I described it, but it's a bunch of handwritten images. It's a really popular image, or really popular task. So it's in a lot of tutorials. It's like one of the quintessential deep learning, machine learning tasks that people cover. But basically, you want to predict, given an image, what number it is. Oops, wrong one. So to do this, since it's such a popular thing, people have already made files that give you the NumPy arrays. And what they actually did for you here is, so an image, you know how image has, in this case, the image has 784 pixels, but they're normally, images are square. But what they did here is they flattened it. So for each row, they concatenate the next one to the end of that, next one to the end of that. So it's, what they're actually giving us is a matrix of 784 spots, and each of those is a pixel value. So it's a flattened out image, basically, and it's telling like the grayscale level of each pixel. So you can see that here. And it's zeros here, because if you think about it, it's looking at the corners of the image, so that's usually like white or blank space. You know, no one's going to write there when they write their numbers, which is unfortunate. That's a bad display. But you see here, there's 50,000 images, and each of them has 784 features. And again, the features are the pixel values. And then here, the labels are what they are. So this is a 5, this is a 0, 4, so on. And again, we can't use these to train. Or you could use like regression, but like that's not what we want to do. We want to do this to categorical function, so that we ultimately put 1 in the corresponding location. So this is a 0, 1, 2, 3, 4, 5, 6, 7. This represents a 7, right? This is a 0, a 2. So we made our labels for you already. We're going to use the same generate batch function, TensorFlow, import that. And so what we want you guys to try and do is create a softmax regression on this data set now, and try to like optimize it and like see who can get the best score. So things you might want to keep in mind is the features are different size. So here we have 784 this time, and we have a different set of labels. So the labels are size 10, not 2. It's not a binary classification. And some things you might want to look at is like learning rate, number of iterations. You don't want to overtrain. Yeah. So now is your time to kind of fool around with this. If you guys need any help, feel free to ask us.